Namaste, dosto. Imagine you're riding a bike down a hill. How do you know how fast you're going exactly at this moment? Not the average speed over the whole ride, but your instant speed at this very point. This is where the magic of derivatives comes in. Today, we'll explore the concept of derivatives, which help us find the instantaneous rate of change. So, what exactly is a derivative? Simply put, derivatives represent the rate at which a function changes at a particular point. You can think of it as the slope of the tangent line touching the curve right there. To understand this mathematically, the derivative of a function f of x at the point x equals a is defined as the limit as h approaches 0 of the difference quotient. That is, f prime of a equals the limit as h tends to 0 of the quantity f of a plus h minus f of a divided by h. Let me repeat that slowly. F prime of a equals limit h tends to 0 bracket f of a plus h minus f of a close bracket divided by h. For this derivative to exist at that point, this limit must exist, which connects the ideas of limits and continuity directly to derivatives. You see, derivatives aren't just abstract math. They are super useful in physics and real life. They give us a powerful way to understand velocity, acceleration, and many other quantities that involve how quickly something changes. So, as we move ahead, get ready to see how this idea of instantaneous rate of change unfolds beautifully through functions and their graphs. Shabash! You're on the path to mastering an important tool in mathematics. Let's smoothly move from the definition to how derivatives look on a graph. Imagine the curve of a function f of x and a specific point x equals a on this curve. The derivative of the function at that point gives us the slope of the tangent to that curve exactly at x equals a. If the function is differentiable at x equals a, that means the derivative exists there. Then f prime of a is the slope of the unique tangent line touching the point a comma f of a on the graph. Here's an interesting point to note. If the tangent is horizontal at that point, then the derivative value is 0. This situation often signals local maxima or minima, places where the curve bends its direction, or even inflection points where the curve changes its concavity. By looking at the sign and value of the derivative near this point, we can also understand the concavity and general shape of the function's graph. Is it curving upwards, like a smile, or downwards, like a frown? The derivative carries these clues. Try picturing a secant line slicing through 2 points on the curve, gradually moving to meet the tangent at point x equals a. This approach gives an intuitive feel of how the derivative captures the exact slope at a single point. Keep this visualization in your mind. It's fundamental to our understanding. Now, how do we write derivatives? There are several notations you'll commonly see, and it's helpful to be comfortable with all. For example, you might see f prime of x, or the more formal differential form dy by dx, saying the derivative of y with respect to x. Another common notation is d sub x bracket f of x, meaning the derivative operator with respect to x applied to f of x. And sometimes, if y equals f of x, simply y prime is used. Moving to some basic rules, the first important one is linearity. The derivative of a sum or difference of functions follows the rule. The derivative with respect to x of a times f of x plus b times g of x equals a times the derivative of f with respect to x plus b times the derivative of g with respect to x, where a and b are constants. Next, the famous power rule states that the derivative with respect to x of x raised to the power n is n times x raised to the power n minus 1. This is valid for all real numbers n except 0. Lastly, the derivative of a constant function is 0. So, the derivative with respect to x of c, where c is any constant, equals 0. These rules are the building blocks for differentiating many functions easily and efficiently. Let's apply these rules to polynomial functions, which you already know well. Take a polynomial like f of x equals a x raised to the n plus b x raised to n minus 1 plus and so on until plus c, where a, b, and c are constants. Polynomials are differentiable at every real x, which means we can find their derivatives everywhere without trouble. The way to differentiate such polynomials is term-wise. Differentiate each term separately using the power and constant rules we just discussed. This gives f prime of x equals a times n times x raised to the power n minus 1 plus b times n minus 1 times x raised to the power n minus 2 plus the rest accordingly. Notice how each derivative reduces the power of x by 1, indicating the rate at which each term contributes to the function's overall change. Because sums and multiples of differentiable functions remain differentiable, these rules make differentiation of polynomials straightforward and systematic. Now, what if our function is not just a simple polynomial, but a product or a quotient of two functions? For these cases, we have special differentiation rules. The product rule states, the derivative with respect to x of the product u of x times v of x equals u prime times v plus u times v prime. Here, both u and v have to be differentiable. Similarly, the quotient rule helps us differentiate ratios of functions. It says the derivative with respect to x of u of x divided by v of x equals the quantity u prime times v minus u times v prime, all divided by v squared, as long as v of x is not 0. These rules expand our toolbox, letting us work with complex functions involving products and ratios comfortably. Imagine a flowchart connecting power, product, and quotient rules. It's like a roadmap you can follow to differentiate many algebraic expressions with confidence. Let's take a closer look at how derivatives come from first principles using the classic example of f of x equals x squared. By the limit definition, f prime of x equals the limit as h approaches 0 of the difference quotient, bracket f of x plus h minus f of x close bracket divided by h. Putting in the function gives us the limit as h tends to 0 of the quantity x plus h squared minus x squared divided by h. Simplify the numerator. X squared plus 2xh plus h squared minus x squared simplifies to 2xh plus h squared. Then dividing by h, we get the expression 2x plus h. Now, taking the limit as h approaches 0, h vanishes, leaving us with 2x. So, from first principles, we see f prime of x equals to x. Notice how perfectly this matches the power rule result for n equals 2. Let's quickly recap what we've learned today. First, the derivative of f of x is defined as the limit as h approaches 0 of the difference quotient, f of x plus h minus f of x divided by h. Second, the power rule tells us that the derivative with respect to x of x raised to n is n times x raised to n minus 1. Third, the quotient rule states that the derivative with respect to x of u divided by v equals the quantity u prime times v minus u times v prime divided by v squared. Key ideas to remember are that the derivative measures the instantaneous rate of change at a point, linking neatly with limits and continuity. First principles help us understand and derive the rules like power, product, and quotient. Geometrically, the derivative relates directly to the slope of the tangent on the function's graph. And finally, these rules make computing derivatives, especially for polynomials and rational functions, much more straightforward. Think about it. Whenever you want to know how fast or how steep something changes, derivatives are your go-to concept. Keep practicing, and soon you'll be differentiating with ease, ready to apply this powerful mathematical tool wherever needed. Shabash.